Welcome to the fourth week of the course Collaborative Robots Theory and Practice. This week will be on inverse kinematics, velocity and acceleration analysis. We'll have 5 lectures in this module. We'll start with introduction to inverse kinematics. We'll continue with analysis of 2R planar arm, 3R spatial arm and SCARA robot. In the second lecture, I'll discuss 6 degrees of freedom wrist partition arm. We'll do inverse kinematics of that. We'll discuss inverse kinematics analysis of UR arm, that is universal robot arms, that is 6 degrees of freedom arm in lecture 3. Before we move on to inverse kinematics of 7 degrees of freedom robots like KUKA IVA robot and discuss on null space, I'll discuss on differential motion analysis. In the fourth lecture, we'll discuss robot Jacobian velocity and acceleration analysis. In the fifth and the final lecture, we'll do inverse kinematics of a 7 degrees of freedom KUKA IVA robot and we'll finally discuss on null spaces. So let us continue with the first lecture of this module, that is inverse kinematics, velocity and acceleration analysis of the course Collaborative Robots Theory and Practice. In this lecture, I will begin with introducing you all to inverse kinematics. I will continue with examples. The first example will be on 2R planar arm. I will do inverse kinematic analysis of that. In the second example, I will do inverse kinematic analysis of 3R spatial arm, and I will continue further to 4 degrees of freedom SCARA cobot or a robot arm, and I will do inverse kinematics of that as well. So let us continue with the introduction first. So what is an inverse kinematics? Okay. So solving for joint variables, that is the joint angle in case of revolute joint robot and joint displacement in case of prismatic joints of a robot for any given end effector pose. Let us say you have a robot like this, okay. You have first link that comes here, you have second link that goes like this. Let us assume it is a planar arm. So if you know the xy, that is the end effector position of this robot, so this is x axis, this is y axis. If you know the position of this, what is my joint angle? So first joint angle that comes here, that is, let us say it is theta 1, the second joint angle is theta 2, link lengths are given L1 and L2. So given the end effector position, finding out the joint angles that will actually take it to that particular position. So solving for these problems is known as inverse kinematics analysis. Okay. Inverse kinematics problem is broadly solved using two major ways, that is trigonometric and algebraic approach, that is using matrix and vectors approach, and the second one is solid geometric approach. We will not be doing this, we will focus on trigonometric and algebraic solution for all the problems that I will be discussing. Solvability: generally all the systems or all the robots with revolute or prismatic joint having a total of 6 degrees of freedom or less in a single serial chain are solvable. Okay. That may not be true for quite a lot of robots, that we will see later. So exceptions are one with several intersecting axes, and systems with more than 6 degrees of freedom normally have redundant solution, or it may even have infinite solution. Those are not solvable. So what is a reachable workspace? So in order to get to a solution first for an inverse kinematics, robot should lie in a reachable workspace. So it is a volume of workspace that the robot can reach in at least one possible configuration. Okay, one possible configuration. It may not be possible that you go there and you can orient it in all the possible ways. So at least one possible configuration it should go there. If robot is in this reachable workspace, definitely we should try for getting an inverse kinematics solution. So this is a robot it is the Kuka-Iwa which is shown here. So these are the joint angles which it has. Okay. So various joint angles are there. So end effector pose will be given and I am required to solve for the joint angles. So in case of cobots, they are mostly having revolute joints and will solve for joint angles. Okay. So let us begin with a traditional problem, that is inverse kinematics analysis of a 2R planar arm. This is one of the most simplest arm which is there in quite a lot of robots as a subset, even if they have multiple links. So any portion of that, it may have a 2-link arm which is like this. Okay, what it is? It is a planar manipulator, just like your engineering drafter as you have seen. Okay, so this is your link 1. Okay, first link goes here and you have a second link that goes like this. So you have an end effector that lies here. Okay, end effector has a coordinate x and y. So this is your x axis, this is your y axis. Okay, this is joint angle theta 1 and joint angle theta 2. Theta 2 is a relative angle. Joint first makes the angle with the horizontal axis, that is with respect to this fixed frame, it makes theta 1. Joint 2 makes an angle with respect to the extension of link 1. Link 2 makes an angle of theta 2. Link lengths are A1 and A2 which is given. So the entire geometry of this system is given, is known. Okay. What additionally is known? Where does it lie? It lies at xy. So now I have to get the output of this inverse kinematics algorithm. So what it is basically the solution of this robot for the given position, that is xy. I need to get the angles, that is theta 1 and theta 2. So this is how inverse kinematics is defined also. Okay, so we'll do that now. So using triangle OAE, where are they? It is O, this is A, this is E. So this is the triangle which comprises of link length A1, link length A2, and you have this is R, this is O, this is A, this is E. If this is the triangle, using the cosine rule, I can get cosine of alpha. Alpha is here, if you can see it here, this is your alpha. Cosine of alpha is A1 square plus A2 square minus R square by 2 A1 A2. Okay, so A1 square plus A2 square minus R square by 2 A1 A2. This is your link angle. Okay, this is the angle alpha. Okay, so moving forward, so from triangle OCE, where are they? O, C and E, that is the end effector position. You know, using Pythagoras theorem, you can get R square is equal to x square plus y square. So this is your x and y. So if I substitute this R square here, what do I get? Cosine of alpha is equal to A1 square plus A2 square minus x square plus y square by 2 A1 A2. Okay. So now since theta 2 is equal to pi minus alpha, you can get it. So this is theta 2 is equal to pi minus this alpha angle. So this is the angle. So pi minus alpha. So cosine of theta 2 is equal to minus of cosine of alpha. So I can just put cosine alpha there. So what do I get? Cosine of theta 2 is equal to this, and theta 2 is equal to plus or minus cosine inverse of x square plus y square minus A1 square plus A2 square by 2 A1 A2. Okay, so now I could get theta 2 for the given position xy and the link lengths A1 and A2. So these are the known parameters. Okay, theta 2 was unknown and we could get it. Please note, so cosine theta 2 is this, so theta 2 will be plus or minus of cosine inverse. Why? Because for cosine minus theta, is also equal to cosine theta. So that is an inverse. So that is what I should be getting. So this is how I get theta 2. Now how to obtain theta 1, that is the joint angle 1. Okay. Now from triangle OEB, OE and B, that is a right angle triangle, you see. Okay. You could clearly note here, yes, if this is A2, so this side will be, this perpendicular will be A2 sin A theta 2. This angle is theta 2. And similarly, AB will be, AB, that is this one is A2 cosine of theta 2. Okay. So now the edge, this is actually equal to EB by OB. How much is OB basically? OB is A1 plus A2 cosine theta 2, that goes to the denominator, and perpendicular is A2 sin A of theta 2. So how much is that? That is equal to tan of beta. So beta is here, beta angle is here. So tan of beta is equal to this, EB by OB. Okay. Similarly, you can get quickly using triangle OC and E again, that is equal to tan of gamma, gamma is here, that is the full angle gamma, tan of gamma is equal to y by x. Okay. So now using these two, I can quickly write beta is equal to plus or minus, again it will be plus or minus, because if it is minus theta 2, you saw in the earlier case it was plus or minus. So if minus theta 2, it will be minus, for plus it is plus. So beta is equal to plus or minus tan inverse of this. So using this, I obtained this. Again from the second one, tan gamma y by x, so I could get gamma is equal to tan inverse of y by x. Okay. So now using these two, I can get theta 1. So theta 1 is here. Okay, that is related to gamma and beta as gamma minus beta is equal to theta 1. So gamma minus beta, beta can be plus or minus. So I can get theta 1 is equal to gamma minus and plus beta. Okay. So theta 1 is now equal to, if I put the values directly from here, I could get theta 1 is equal to this, and from the previous result we got already theta 2, that comes like this. Okay. So you see, this points out that these two actually points out to a multiple solution. For plus and minus, you have at least two solutions, that is clearly visible here. Can we reach there? Now let us understand the multiple solutions. So you got what? You got theta 2 is equal to plus or minus cos inverse of this, and beta is equal to this. So you can now clearly see here, this is the plot of cosine. When you see here, you see you have cosine having two different values. For the value like cosine of plus or minus of theta leads you to the same value. Okay, that is the same value. Okay, these are leading to the same positions. Okay, so now what does these two solution mean? You see, first of all, theta 1 is equal to gamma minus plus and minus beta. So gamma plus or minus beta becomes gamma minus plus beta, and theta 1 is equal to this. So you see, one of them is actually gamma plus beta. Okay, so that is your theta 1. In second case, it is gamma minus beta. Okay, so that becomes equal to theta 1. So these are the two cases. Okay, so when theta 1 is like this, configuration of the robot is like this. So in that case, theta 2 is negative. Okay, so when it is in this position, okay, so theta 2 is positive. So one of them is positive, other one is automatically negative. So in this case, it is known as elbow up solution, and this one is elbow down position. Both of them are located at same end effector position, that is xy. Got it? So for the same xy position, it could be either elbow down or elbow up case, okay, depending on the solution. So you see, right at the first example, you could notice that even a two link system can have multiple solutions. Okay. Now let us see some of the problems that is arising because of arc cosine and arc sine A solutions. So you saw here this one was tan A solution, but theta 2 has cosine solution. So what is the problem with this? So the accuracy of arc cosine function in determining the angle is dependent on the angle itself. So as you see, it is cos minus theta is equal to cos theta. So the solutions are ill conditioned and inconsistent because of this. In programming, when you start programming for inverse kinematics, you should be very particular about the solution and the system should be well programmable. Can we put any condition so as to get to the accurate solution, exact solution? So that is the reason it should be well defined. Okay. So in case of sine A, you see, sine A approaches to 0 for theta nearly equal to 0 or nearly equal to 180 degree. So this give an inaccurate solution and again they are undefined at times. Okay. So you see, again using sine A would also be a problem. So what is the solution for this? Okay, that we will see. So please note again, solution for inverse kinematics is specific to any particular architecture of the robot. Okay, if a robot is inline robot like KUKA IVA, or it is a robot like UR-arm or like in standard industrial arm, so each and every robot has its own solution until unless they are kinematically similar. Okay, only the dimensions are changing, then you can use same general solution, but there is no general solution in case of inverse kinematics of a serial robot. Okay, each robot may be a different one and you need to solve them independently. Okay, so now let us move and see how that sine and cosine issues can be solved. So now you saw I attempted to get the result in form of tangents. So you see, in case of tangent you can put conditions. Okay, let us say you have all sine, tan and cos. Okay, so tan is positive here, tan is positive here, otherwise it is negative. So based on the location of your arm, if your arm is located here, so it is plus for x and y. If it is here, it is having a different scenario, so it is negative and positive for x and y coordinates. So depending on the different quadrant of your arm location, you have a different result for tangent, and this can be easily set in case of tangent, because tangent are directly governed by x and y coordinates, unlike sine A where it is y by hypotenuse. So hypotenuse do not change its sign, only y will change its sign. So you cannot put the condition to it. But in case of this, you can clearly understand if it is in, if the robot arm is in positive quadrant or in the second quadrant, third quadrant or fourth quadrant. So depending on them, you can clearly define your theta using programming also. So these are the conditions that you can put depending on positive of x, theta lies here. So because you see tan theta is equal to y by x. Tan theta will have same value for plus of these two, plus x and plus y, minus x and minus y, it will have same value. So if tan value is same but the input values for x and y is in different quadrant, you should get different values for theta. Okay, so that is quite easily possible using these type of conditioning. Okay, so in this case it is known as A tan 2 solution, and it is a ready-made function available in quite lot of programming language like MATLAB or Python libraries. It is inbuilt function. So this accounts for full range of angular solution, also known as 4 quadrant arc tangent solution. So these are the conditions, you can go through this, and each condition for y less than 0, you have to consider this value of theta. Okay. For y greater than and x less than this, both are greater than equal to 0, you can take directly. Again, there are some explicit condition in which one of them becomes equal to 0, especially the denominator. So, when denominator is equal to 0, you can have solution like it is either over here or here. So, in that case 90° or plus 90°, you can directly check the condition without evaluating the tangent, and you can write it as plus pi by 2 or minus pi by 2. In case both of them are 0, you need not to evaluate, you directly it is undefined. Okay. These are the plots for tangent that I have shown, and the quadrants also. Okay. So, you try to get the solution in tangent way, so that it can be programmatically made unambiguous. Okay. Okay. Now, let us move ahead for my second example, that is inverse kinematic analysis of 3R spatial arm. Okay. So, we have already done forward kinematics of that. So, you can already directly get these equations from there. Okay. So, what is it directly? So, you can directly even get through trigonometric projections. So, this is the arm which looks like this. I will just show you once here. Okay. So, this is the first joint which is moving. Okay. It is coming back. This is the second joint. Okay. This is axis of motion is parallel to the ground plane, and the final one is the, again it is an axis which is parallel to the ground plane, that is for the joint angle 3. Okay, third joint. So, yes, so this is x, this is y, this is z. I can obtain them directly using trigonometric projections also, but I have just copied it from the forward kinematic solution. So, you can check it. So, this is what x is here. How much is that? So, you see this is the 2 arm planar arm which is link 2 and link 3 that lies always in a plane, and the plane rotates about the axis 1 by an angle theta 1. Okay, so this lies in a plane. So, this is a plane. Okay. So, this arm will always lie in a plane. So, this is a planar 2R arm with link length A2 and A3. Okay, theta 2 and theta 3 are the joint angles. Okay. So, Ex dash is here. So, Ex dash is equal to A2 cosine theta 2 plus A3 cosine theta 2 plus theta 3, and that is Ex dash. And similarly, Ez dash over here, instead of y along the vertical axis you have z. So, Ez dash is equal to A2 sin theta 2 plus A2 sin theta 2 plus theta 3. Okay. So, you got Ex dash and Ez dash. Okay. So, those two are the coordinates for this 2R planar arm in its own base frame, that is O dash. Okay. Now, using Ex dash, that is this one. So, if I project it along x axis, I get this cosine theta 1, that is x, first equation. Similarly, sin a theta 1 will be second one, that is y, and z will be sum of this vertical distance plus from here to here. Okay. So, it went little clumsy. So, this is the clear one for the same. Okay. So, this is how you can directly obtain through trigonometric projection, or you can directly do it using forward kinematics. So, this is how the link lengths, joint angles and the end effector positions are related. Now, what is given is x, y, z, that is location of end effector position. I have to find out the joint angles theta 1, theta 2 and theta 3. Okay. Okay. The first two equations, equation 1, equation 2 and equation 3, from the first two I can quickly write theta 1 is equal to tan inverse of y by x. If I divide the second equation by first equation. Okay, so y by x gives me tan of theta 1. Again theta 1 would be equal to a tan 2 y comma x. So you have to use arc tangent here to get the angle theta 1. Okay. So now again using theta 1 I can write, I can substitute theta 1 here and here, and I can write Ex dash is equal to x by cosine theta 1. Similarly, from this equation I can write z minus d1 is equal to Ez dash. So that is this distance Ez dash and Ex dash. What I am trying to get is basically the local coordinates, that is Ex dash and Ez dash, that is the end effector x dash and y dash in this plane, okay, this plane, so that I can consider this subset as a 2R planar arm and I can solve for joint angles theta 2 and theta 3. So in order to solve this, this becomes a local 2R manipulator and I will solve for it. So these are the coordinates for that, okay, for this 2R manipulator. So this is equivalent to now a 2R arm with links 2 and 3, okay, in the plane x dash z dash. So where are they? This is your x dash and this is your now z dash from here. So now I'll use this and solve for this. So using this 2R planar arm solution that we have done earlier, I will simply put Ex dash and Ez dash in place of x and y and I can get theta 2 and theta 3, okay, that is this angle and this angle, okay, and I could get all the angles. So theta 1 was equal to tan inverse of y by x, theta 2 and this is theta 3. So all the joint angles are solved. So the second subset is very helpful here. You have already solved this one actually, 2R planar arm. So I have used it directly here and same will be doing it for many other arms also. Okay, so 2R manipulator is very important and that helps us to quickly solve many other robots as well as the way we have done it here. So now how many solutions does it have? You have already seen second link and the third link can have two positions. This is elbow down which is drawn here. This could be elbow up position. Okay. Again theta 1 could be theta 1 or pi plus this theta 1. Okay. Is it not? So this can be right at the front or you can go 180 degree behind. Theta 1 goes 180 degree behind from the existing position and from behind you can do elbow up and elbow down. So total there are 4 solutions. So this is how you need to evaluate any given solution for multiple solutions also. Okay. Now let us see what is an SCARA robot. Okay, this is one of the most popular kind of robot which is there in the industry. I'll just quickly switch to that window and try to show you here. So this is a standard SCARA robot. So you see it has first motion, it can do like this, that is the revolute axis, that is perpendicular to the ground. Second one is something like this, again it is perpendicular to the ground where it is attached. Okay, the first and the second axis are parallel to each other and the third one also is perpendicular to the ground and it is prismatic this time, it goes up and down in linear way. Okay, so it is linear displacement. Okay, and the fourth one is revolute axis again. So you have at least 3 revolute axes here and all the axes are parallel to each other and perpendicular to the ground. Okay, this is a standard robot. So in this case what you can see here, why this robot is very popular, because it can do, see, all the motors for the first and second axis lies at the ground. Okay, and the second joint is connected mostly using a belt. So you have low mass which is moving. So both the motors are situated at the fixed base, okay, over here, okay, in the fixed base. So that makes it very lighter, okay. So they are having less moment of inertia, so it can have very high speed, okay. They have very high speed and it is not getting influenced by the gravity, okay. So you can put it anywhere and gravity doesn't affect any of the joint torques, okay. So you don't have to move against the gravity anywhere except the prismatic link, that is only affected by the gravity. All the three rotary axes are free from gravity, okay. So that is the reason they are very fast, they are very quick, they have low moment of inertia. So that is the reason it is very popular in the industry for pick and place, vertical pick and place operation in the industry, like, okay, PCB assembly thing. So you can pick up a chip, you place it on the board, you just need some motion like yaw motion, okay. You don't need many other motion. So this is the yaw motion to orient your chip. It can pick from a place and it can put it anywhere, okay. So you pick it, you place it, pick it, place it, so that way it is very, very fast. So the robot that I am going to show here now is a different kind of SCARA in which the prismatic axis at the first joint. So I'll just show a small quick video. In this case, you see the first joint is a prismatic axis, okay. Second, third and the fourth one are revolute axes, okay. Both are equally good. So this is the first and second joint shown in motion. So this is second and third axis which is shown in motion. So you see it shows all the axes here. This is second joint moving, first joint moving also. So this is how it can operate. So only difference from standard ABB SCARA robot is it has first axis which is prismatic, okay. Both are equally good, we'll see using the kinematic equation also, okay. So let us come here. So this is what is your SCARA. Again, let me just show you the technical specifications of this. You can see it. So yes, so you see the first axis, this one from here to here. So this is your linear axis, this goes up and down. So you have another one which is a prismatic axis and a revolute axis which is here. You have revolute axis here and you have revolute axis here. So three are revolute axes. First one is prismatic joint. Got it? This is how it looks like. So these are the specification. Nowhere it is written which standard does it follow. I don't know if it is a purely a cobot, because a cobot has to follow ISO 15066, okay. So that standard is not mentioned here. So any robot which allows you moving by hand is not a cobot, okay. So mind it. So this may not be a cobot because it doesn't mention its standards which it follows, okay. It may not be safe for human all the time. So yes, but because it is a low powered robot and a desktop robot, may be safer, okay. So now let us go and do inverse kinematics for this. So inverse kinematics of SCARA, again I will start with the forward kinematic equation that we have obtained earlier. So this is your forward kinematic equation, okay. For the end effector homogeneous transformation matrix is written here, that gives you the orientation and position of your end effector frame with respect to the base, okay. So what is known is end effector pose, that is position XYZ of this end effector, and orientation, okay. This robot can not only go to any XYZ because it is a 4 degree of freedom robot and you have a rotation. So this last frame can also have a rotation axis, okay. So that is the angle psi. So that is written here. Okay, so you have to give the complete configuration of this robot by mentioning the end effector position and the angle psi. Okay, what is to be obtained is joint variables, that is theta 1, theta 2, d3 and theta 4. In case of this robot, the one which is shown here, d3 is over here, this is the prismatic joint. But in case of the other Iskara, that is the Dobot, okay, you have d1 which is variable, equally good, both are vertical axis, so you have only one vertical displacement. So it doesn't matter if it is at beginning of the robot or at end of the serial chain, at least in this case. Not always true, but in this case you can have either one of them as a prismatic joint and it is equally good. Okay. So now using forward kinematics, I can quickly write this over here. So you have x, you have y, you have z, which is x, y, z, and you have psi, which is nothing but sum of all the angles. So that is theta 1, theta 2 and theta 3, sum of all the angles will actually make it to psi. But in case of theta 4, it is actually counterclockwise, which is positive because it is pointed downwards. So if you look from the top, it is like this. So that makes it negative here. Okay. So now I'll use this to solve the inverse kinematics. So if I look it from the top, what do you see? What do you see here? So it looks like a 2R subsystem. Okay. If I look it from the top, if I go back, okay, what do you see? From top you see A1 and A2 are the link lengths for which theta 1 and theta 2 are the joint angles. So whatever is the position of my end effector, same is the position of P2 point, which is vertically above the end effector. Is it not? If you look it from the top, it becomes like this. Okay, so in this case it is exactly equal to the same coordinate which is there for the end effector. Okay, so if it is xy here, so this also will have same coordinate xy over here. So this is again a 2R subset, as Z2 is along Z4. So Z4 and Z2 are in a same line. Okay, so that makes it like that. So this is it. So now you can quickly obtain, so you already have solved for it. A1 and A2 are the link lengths. Okay, you have theta 1 and theta 2 are the joint angles. They can quickly be obtained using 2R subset again, and you got this. How much is D3? So you see, if you just go back and see your slide, so only D3 is variable. D3 is, D1 is constant, D1 is constant, okay, D2 is also constant, which is not varying, okay, D4 is also constant, which is here, okay, D1, D2 and D4 are constants, those are not varying. So what is varying is only D3, and that is making the change in Z. So if I write it here directly, so I can write D3 as, D3 is equal to D1 plus D2 minus D4 minus of Z. Okay, or if it is in case of Dobot, I can write it like this. So in that case you have D1 which is variable, and you can write it like this. So this in case of Dobot, this in case of ABB robot that I have shown. Many other industrial robots are of this kind only. Okay. Now if you have to get theta 4, you can quickly write. So it is equal to theta 1, theta 2 and the final angle that you also had, that is the variable one, theta 4. Psi is already given, that is the end effector orientation was given, okay, the yaw angle. So you just use it and you can get theta 4. So you have solved for theta 1, theta 2, D3 and theta 4. So this is how a Iskara robot is solved. Okay. So that's all for this lecture. In the next lecture, I'll discuss inverse kinematic analysis of a 6 degrees of freedom robot, which is wrist partitioned arm. Okay. Thanks a lot.